last night I got a bunch of uh, suggestions for improvements on the row combinator paper, um, and I have uh, put the bulk of them into the paper. It's in GitHub. Folks are free to download the repository. It's in the name-free combinators for the row calculus under Pi for You in the RChain repo. So that's all done. We're resubmitting it to Places 2020, which is in Dublin this year in April. So that's what's going on with the Casper research. It's the first name-free account of combinators. That doesn't have a global name generation service. So apparently in '90s, we didn't know this until I guess the last time we submitted the paper. We found someone had done a version using the techniques of Quine, which is a little different than the way the standard way that Honda and Yoshida did the abstraction elimination. There are basically two things you have to eliminate when you're eliminating names from Pi. It's unlike Lambda, right? Lambda has only one kind of name, and that's really just the variable for Lambda abstraction. But Pi has two kinds of names, right? One is the variables from the input guarded processes, and the other is the new binder, which you can treat as effectively a decomposed into an input and the supply of a globally unique name. But we don't do it that way. We don't treat it as a globally unique name. We can with reflection, we're able to calculate from the given scope a name that is fresh with respect to that scope. So we can, at compile time, generate just what's necessary for that scope, and then it's always going to be globally unique at the end of whatever your translation or compilation process is, because it's when you're done with your compilation, you've run out of scopes. So as you're either descending or ascending up through the scopes, you generate names that are fresh with respect to that scope, so they keep being fresh. And so that's the trick. So it's different from that process. And then the utility of this, I mean, it has utility in and of itself, right? Because then you don't have to deal with nominal phenomena. You have a model of mobile concurrent computation that doesn't use any names. So that's about as simple as you can get, which means you can now reason about these kinds of phenomena without all the extra machinery necessary to deal with names or variables. But for us, having that allows us to present the ladle algorithm without having to deal with the extra machinery of variables. So that's why it's useful for us specifically. We can like the issue, as I've said many times about this, is that when we do the distributive law approach demands that you've got these monads But if you've got variables, then it's not clear how to treat that monadically. I mean, there's a couple of approaches, but essentially you're going to have to compose a couple of monads, and that ends up being a lot of extra work. But if we can compile away all of that, then we can demonstrate the Ladle algorithm for a full-featured model of computation, in the sense that it's got, mobile concurrent computation. So all of those features plus metaprogramming, reflection, and the type system. So that's the trick that's going on there. So that's how all the pieces fit together.
May I just ask about this name you're generating? You need two separate groups of names, right? I'm thinking in a sense of even and odd numbers. If you have numbers, you're choosing two groups. Like, does this make sense?
Yeah. So it's not that we need two groups of names. It's that there are two different phenomena that we're modeling. One has to do with variables associated with abstraction, right? So if you have lambda x dot m, then that's exactly the same as lambda y dot m, where you substitute y for x under the assumption that y is not free in m.
Yep.
Right? So there's no specific name that abstraction refers to. It's just a placeholder. It could be any name, right? And the elimination of that name is done via the standard tricks that you get with SKI, right? So, and that's similar to what Honda and Yoshida do with their combinators, right? So they're effectively doing an abstraction elimination. So that procedure is well known and has been known since the 1930s, right? So almost 100 years now. Right? So it's a well-known algorithm, but Honda and Yoshida were not able to get rid of the new binders, right? So so the new constructor was different. And one trick that was used by S. Raja was to, essentially have a global name service that everybody goes to. So one centralized global name service that's responsible for generating a globally unique name.
I see.
And that's a solution, but it's not a very pretty solution, in the sense that you have this centralized authority that's handing out names, right? And that's that has all kinds of implications for performance and compositionality and all of that stuff, right? So it's not a good solution. The other the approach that we have is that we are able to guarantee a property, and that property is that no process can contain a name that contains the quote of the process.
I see.
So you
have many different groups. In each branch is different group of names. Is this make sense?
Yes, that's correct. So if I have process P, then P cannot contain a name that has a quote P in it. So you can build a name that is guaranteed to be fresh for P simply by quoting P and then doing something to that. Right? And so now you have a compilation strategy that does not require having a global view, globally unique names. So you can do this, you can do this in pieces. And once you can do it in pieces, then you get a much better approach, right? And in fact, what we do is we do it at compile time, right? So the other approach needs a runtime service to hand out the names. We don't need a runtime service. We can do this once and for all as a compilation.
And this is par generator that we have in our chain, right? Random par generator.
The par generator is related, but it's not the same.
Yeah. Oh, okay. Is the par generator like implementation of this, or?
I don't remember what Kyle did. It's been a few years since I looked at what he did.
Okay.
But the main trick is that, once you know the idea, you can have all kinds of variants of this idea. So that's how all the pieces fit together, and they turn out to be really important, right? They're important from the point of view of just foundational stuff. Right now we know that there is a combinatorial approach that has all the features and is compositional. Right? That answers some really important questions. Those are foundational questions in computing, right? And then, but also once we have that, then we can apply the ladle algorithm without a lot of mess and fuss. We don't have to worry too much about the nominal phenomena. We just we got this simple Levier theory, and a graph enriched Levier theory that we apply the ladle algorithm to, and we generate a type system, and the type system has all these wonderful rich properties that we've discussed many times before. So that's really important. It's interesting. I was listening to yesterday morning. I was listening to this talk given at the Princeton Institute for Advanced Studies. So that's where Einstein ended up, and Gödel ended up, and all the luminaries of the 20th and 21st century. They do a stint at the Institute for Advanced Studies. So it's a highly respected institution, and the talk given at the institution was sort of the mathematics out for the next 10 years. So mathematics from now until predictions for the development of mathematics in 2030. And so the speaker was giving a lot of good information for practicing mathematicians who haven't really taken on board all of the internet tools. So he was talking about GitHub and lots of basic things, but then he moved on to sort of future stuff, and one of the things that he talked about was mathematical search. So there are all kinds of interesting mathematical databases. For example, the online encyclopedia of integer sequences, right? So that's a really fun one, and I've learned about some really cool sequences through number files probing of the online encyclopedia of integer sequences. And there are many other mathematical databases, and you can even think of Wikipedia as a kind of mathematical database, in the sense that there's lots of mathematical knowledge that's stored in Wikipedia. And he began asking, well, how do we do mathematical search? Search where we don't necessarily know the exact names of things, right? Because maybe somebody uses the variable p and somebody else uses the variable q and somebody else uses the, you know, the variable m, but it's all the same definitions, right? Or the definitions are slightly variant, right? They're, you know, different ways of parsing out the material, leading to slightly different definitions, but ultimately it's the same material. So that's a really interesting topic, and this is the kind of thing I've been talking about now for 20 years, which is how do you search code, and how do you search code on the basis of its structure and what it does, rather than on the basis of keywords used in the code, because different people may name variables differently. They may do slight refactorings of code and that sort of thing. So it's exactly the same idea, but for code, which is arguably our biggest, richest mathematical database, right? I mean, the upshot of Curry Howard is that ultimately every program is a proof. Now, unless you have things worked out nicely, you don't know what it's a proof of, but it is a proof. So all code is essentially a mathematical object, and the question is how to find code on the basis of decent criteria, and that's where Ladle comes in. So Ladle provides a mechanism for that query mechanism, for that query capability, and that's because you can view types as classifying things, and type checking as a filter, right? So you only get the programs that match the types. So that's so it's good to begin to see that other people are thinking about this problem. It's great, and I hope that people begin to realize that there's some really, really good techniques that are available for precisely this thing. All right. Well, that's my updates for today, this Martin Luther King Day. Be free, everyone.
Thank you, Greg.
Thank
you for the updates.
Sure. All right. Ciao for now.
See you. Ciao, ciao.